Picture a Boeing 747 descending toward the runway. It weighs nearly 400,000 kilograms. It falls out of the sky at almost 270 kilometers per hour, and the only thing between that machine and the concrete is a set of rubber tires. When those tires touch down, they go from 0 to full rotation in less than a single second. The rubber screams. Smoke pours off the surface. The temperature at the contact patch spikes toward 200 degrees Celsius almost instantly. Every landing looks like a small violence. The tire is slammed, twisted, heated, and crushed all at once. And yet it does not burst. It does not shred apart across the runway. This is the question that sits under every flight. How does a piece of rubber survive being punished this hard, this often, without failing? Because the stakes are not small. A single main gear tire on a large airliner carries a load of over 20 metric tons. The internal pressure inside it can reach 200 psi, roughly 6 times the pressure in your car tire. That much force, that much heat, that much weight resting on rubber, it sounds like a recipe for an explosion. But airplane tires almost never explode on landing. The failure rate is extraordinarily low. Airlines complete tens of thousands of landings for every serious tire incident. That reliability is not luck. It is not even mostly about the rubber you can see. It is about what hides inside the tire, and the gas that fills it. To understand why these tires hold, we first have to understand what an airplane tire actually is. Because it is nothing like the tire on your car. An airplane tire looks simple from the outside. Black rubber, a few grooves, nothing dramatic. The truth lives underneath the surface. Inside that rubber sit layers of reinforcing fabric called plies. A ply is a sheet of strong cords, often made from nylon or aramid fibers, bonded into the tire body. Aramid is the same family of material used in bulletproof vests. A car tire might have 2 of these layers. An airliner tire can have 30 or more, stacked and wrapped around the wheel like the pages of a book. These plies are the skeleton that holds the pressure in. The tread you see is only a thin skin. The strength is in the structure below it, engineered to resist being pulled apart no matter how hard the load pushes. That is why the pressure can climb so high. At 200 psi, the tire is holding back an enormous outward force. The plies distribute that force across the entire body, so no single point takes the whole strain. The rubber compound itself is also tuned. It is built to flex, to squash flat under the aircraft, then spring back. Engineers call this deformation, the ability to change shape without cracking. A tire that could not flex would crack under the first hard landing. A tire that flexes absorbs the shock and keeps its integrity. These tires are also retreaded. A single carcass can be resurfaced and flown again and again, sometimes hundreds of landings across its life. So the tire is really an armored, layered pressure vessel wearing a rubber coat, but even the strongest structure needs the right thing inside it. And that is where the gas becomes the hero of the story. Here is the detail most people never learn. Airplane tires are not filled with ordinary air. They are filled with nitrogen. Nitrogen is a gas that makes up about 78% of the air you breathe. But in a tire, it is used almost pure, with the oxygen deliberately stripped out. Why does that matter? Because oxygen is the problem. Oxygen supports combustion, meaning it lets things burn. At the extreme temperatures a landing generates, ordinary air inside a tire becomes a fire risk. Think about the heat. The brakes on a large aircraft can glow at over 500 degrees Celsius after a hard stop. That heat radiates straight into the wheel and the gas inside the tire. If that trapped gas were normal air, the oxygen could feed a fire from within or accelerate a violent rupture. Nitrogen refuses to burn. It is inert, meaning it does not easily react with other substances. So the tire is filled with a gas that stays calm under fire. It also holds pressure more steadily as temperature swings because it contains almost no moisture. Water vapor expands unpredictably when heated. Dry nitrogen does not. This is why every commercial airliner uses nitrogen inflation as standard. It is not a luxury, it is a safety rule. But engineers went further. They assumed the tire and wheel could still overheat dangerously, and they built a last line of defense directly into the metal. Because even a fireproof gas inside an armored tire still obeys physics. Heat raises pressure. Pressure has a limit. And what happens when the wheel gets too hot to trust? That answer is bolted into the wheel itself. The most important safety feature on an airplane wheel is not the tire. It is a small plug most passengers will never see. Engineers call it a fusible plug, sometimes a thermal fuse. Fusible means capable of melting. It is a tiny metal insert, screwed into the wheel, filled with a special alloy. That alloy is designed to melt at a precise temperature, often around 175 degrees Celsius. Below that, it stays solid and seals the wheel perfectly. Above it, the metal core softens and gives way. Here is the beautiful logic. If the brakes overheat during a hard landing or a rejected takeoff, that heat soaks into the wheel. The pressure and temperature inside the tire climb toward the danger zone. Before the tire can burst, the fusible plug melts first. It opens a controlled channel. The nitrogen inside escapes in a steady, managed release rather than a violent explosion. The tire simply deflates. A flat tire is a manageable event. A tire explosion at high pressure is not. This single component transforms the failure mode. Instead of shrapnel, you get a hiss. Instead of catastrophe, you get inconvenience. A rejected takeoff is a moment when pilots abort at high speed and brake with maximum force. The brakes can reach terrifying temperatures. The fusible plug is the guardian for exactly that instant. So the modern airplane wheel is a system. Reinforced plies to hold the load, nitrogen to resist fire, a melting plug to prevent explosion. Each piece covers the weakness of the others. And when you understand how they work together, the fear of a landing tire suddenly makes very little sense. Which brings us to what this really means for you. So the next time you feel that hard thump on landing, remember what just happened beneath you. A tire spun from 0 to hundreds of kilometers per hour in an instant. It absorbed the weight of a building, it heated to hundreds of degrees, and it did exactly what it was built to do. That thump is not damage. It is design working perfectly. It is decades of engineering compressed into a fraction of a second. The fear of a bursting tire is a fear of the wrong thing. The system is layered specifically so that the worst case is not an explosion but a slow, safe deflation on the ground. Think about the numbers again. Loads over 20 tons per tire, pressures near 200 psi, brake temperatures above 500 degrees. And still, tire failures serious enough to matter are astonishingly rare. That rarity is earned. It comes from aramid plies, from pure nitrogen, from a plug engineered to melt at a chosen temperature and save everyone from the alternative. This is the quiet truth about modern flight. The parts you never think about are often the parts working hardest to keep you alive. The airplane tire is a small masterpiece of anticipation. Engineers imagined every way it could fail, and then built the answer into the metal and rubber before you ever boarded. You do not have to trust the tire on faith. You can trust the physics, the materials, and the fuse that stands ready. So the tire does not explode because it was never designed to. It was designed to survive. That is the whole secret sitting under your feet.